Chapter 6.2 is going to be the definite integral and the net change of a function. So starting with the definite integral, before this we did the indefinite integral. So the difference here is now we're going to have these bounds on the integral or these limits. So we are going to be taking the integral of a continuous function over an interval a to b. And whenever we have these limits, it's called a definite integral. And there's going to be no plus c after we integrate. So when we take the integral here from a to b of f of x dx, we're going to get the integral function f, capital F, whatever that happens to be. So we integrate f of x, we get this other function. And then what we're going to do is we're going to plug in the limits. We're going to plug in the upper limit and do f of b, and then we're going to subtract f of a, which is the lower limit. And another way that we can write this right-hand side here is right down here. It's going to be the integral function f of x, and then we can write it like this with the little vertical line, evaluated from a to b. And that just means we're going to do f of b minus f of a. And this is also the net change of the function, but we'll be coming back to that later. All right, let's do a couple examples here. So we want to evaluate the integral from 1 to 2 of the function x dx. So let's go ahead and just integrate x. So we're going to add 1 to the exponent and then divide by that new exponent. And we are going to evaluate that from 1 to 2. So we just took the integral, and now we're going to be integrating that from 1 to 2. That means we plug in 2, and then we subtract when we plug in 1. Now we plug in 1. So upper bound minus the lower bound, and that gives us 4 over 2. So 2 minus 1 over 2, so 1/2, and that gives us 3/2. So we integrate and then plug in the bounds, upper bound minus the lower bound. And for now, we're going to say that this represents the net change of the function, f of x, capital F of x. Yeah, let's do another one. Let's evaluate the integral from -1 to 1 of e to the negative t dt. So for this one, we have a exponential, so we're going to recall the integration rule. If we're integrating e to the kx, that's going to equal e to the kx over k. And I'm just going to write plus c because technically what I wrote right here was an indefinite integral. Okay, so this is going to be e to the negative t over -1 because our k value here is -1. We're evaluating this from -1 to +1. And I'm just going to rewrite this as negative e to the negative t from -1 to 1. And now we plug in the upper bound, so negative e to the -1 minus plug in the lower bound. So plugging in the lower bound, -1 is +1. And let's clean this up a little bit. That's going to be negative e to the -1 plus e. And we can clean this up just a little bit. We can rewrite this with the first term being e, and then minus, instead of e to the -1, we can rewrite that as 1 over e. And you could plug that into the calculator if you want, get a decimal answer, but you would have to round, so I'm just going to leave it just like this. So something, before I move on to the next one, something that you could do here is, let's say we're at this step right here. You can factor out the constant. In this case, it's a negative. So it'd be negative e to the negative t from -1 to 1. And then when you're evaluating it, you could evaluate it with that constant, the -1 out front, and you would get the same exact thing as what we just got. But sometimes it might be a little bit cleaner to factor out the constant before you plug it in, before you plug in your limits. Next one, we want to evaluate the integral from 0 to 1 of e to the 2x minus 1 over e to the x dx. So before we even do anything here, we want to rewrite this. So this is going to equal the integral from 0 to 1. We can split up this fraction. We can give each term in the numerator its own denominator of e to the x. So that's going to be e to the 2x divided by e to the x minus 1 over e to the x dx. And we just need, let me clean that up a little bit, we need parentheses around this. So we throw parentheses around it, and then we're going to integrate both of, well, first we can actually simplify just a little bit further here. So it's going to be the integral from 0 to 1, and e to the 2x divided by e to the x simplifies to just e to the x. Common bases, you subtract the exponents. 2x minus x is 1x. And for the next one, we can rewrite that as e to the negative x, because 1 over e to the x is e to the negative x. And now what we can do is we can go ahead and integrate these both separately. So the rule is actually, it's right down here, which we'll come back to in a second. So integrating these both separately, that's going to be the integral. And the reason why we can do these separately is because they're separate terms. They're separated by addition or subtraction. So the integral of the first one minus the integral of the second one. And that's going to be the integral of e to the x is just e to the x. It's itself. Evaluate that from 0 to 1. Minus the integral of e to the negative x is e to the negative x over negative 1. Evaluate that from 0 to 1. And we could put this back together and just evaluate the whole thing from 0 to 1 in one big chunk, which actually is what I will do. So I'm just going to rewrite this as e to the x plus e to the negative x, evaluate from 0 to 1. So all I did here was I just kind of rewrote it. Instead of doing them individually, we're going to do them all together. And then I just rewrote this. Instead of minus the negative 1, I made that positive. So let's go ahead and plug in now upper bound minus lower bound. That's going to be e to the first power plus e to the negative 1 minus, now we plug in 0, e to the 0 plus e to the negative 0. And I'm just going to move this up a little bit. And we have to simplify it. That's going to be e plus 1 over e minus e to the 0 is 1, e to the negative 0 is just e to the 0, so that's also 1. And simplifying this, it doesn't really look too clean. It's e plus 1 over e minus 2. Once again, you could type it in the calculator and get out a nasty decimal. I'm just going to leave it just like this. Okay, so here are the properties that we actually just kind of used. First one is if you're taking the integral of things being added, you can chop them up and give each term its own integral and then add the result. It's kind of like distributing the integral, if you wanted to think of it that way. Same thing for subtracting. You can take the integral of both of the terms separately. And then the other one is if you have a constant on your function, you can bring the constant out front and just multiply it out front and take the integral separately. Okay, so those are 3 important properties. And hopefully those seem kind of obvious. The next 2 are ones that might not seem as obvious just by looking at them. So if you have an integral from a to b, if you switch the bounds and you go from b to a instead of a to b, the answers are going to be equal, except they're going to be the negative version of each other. And then the other one is if your lower limit and your upper limit are the same. So I'm using bound and limit interchangeably. If your lower limit and upper limit are the same, then your answer will always be 0. Next example, let's use these properties that we just went over to evaluate these integrals. So we have these two integrals. We have this one, and then we're subtracting this one. So what we can do is use those properties and recognize that their limits are both from 1 to 3. So we can end up combining these into one integral and just evaluating the one integral. Also, let's go ahead and notice that there is a 2 here. We can multiply this 2 inside of this first one, which we have to do before we combine the two integrals into one. So let's go ahead and just rewrite this first one, the integral from 1 to 3, 6x minus 18x cubed dx minus the integral, and then notice that I'm taking care of this 2. It's going to be 2 times x minus x cubed. I'm going to distribute it. That's 2x minus 2x cubed, just to save a step so we don't have to rewrite it again. And now let's go ahead and combine these into one integral. So it's going to be the integral from 1 to 3 of 6x minus 18x cubed minus the 2x minus 2x cubed. Notice that I had parentheses around that second one because we're going to have to distribute that negative. So that's this negative right now. Let's go ahead and distribute it. And let's distribute and combine like terms in one step. So that's going to be 6x minus 2x. That's going to end up giving a, let's write this in order actually. Let's write this in order in standard form for polynomial. So we have negative 18x cubed minus negative 2x cubed. Negative 18 plus 2, we get negative 16x cubed. And then we have 6x minus 2x, so plus 4x. So that is what we're integrating now, which obviously looks a lot easier than what we started with. So let's go ahead and integrate. And integrating this, we integrate each term separately. So for the first one, we add 1 to the exponent, divide by that new exponent. Second one, we add 1 to the exponent, divide by that new exponent. And then we're evaluating this from 1 to 3, but obviously let's simplify before we plug in. That's going to be negative 4x to the fourth plus 2x squared from 1 to 3. And now we can go ahead and plug in. So we plug in the 3 first, the upper bound or the upper limit. So negative 4 times 3 to the fourth plus 2 times 3 squared minus, now we're going to plug in a 1, negative 4 1 to the fourth plus 2 times 1 squared. And we get negative 324 for that first term plus 18 for that second term, and then minus, we get negative 4 plus 2. So this gives us negative 306 minus a negative 2, which is plus 2. So we get negative 304. Okay, so a little bit longer, just using those properties, combining it into one integral and making it a little bit easier for us. Now, the next one here, we have a new rule, and that's integrals over adjacent intervals. And before I take a look at what it actually says here, let's take a look at a number line. And let's say we have some number line, and it's from A to B. And now let's introduce some new part of this number line that's in between A and B, and we're going to call it C. So hopefully you agree with me that this value plus this value equals the total interval. That's going to be the interval from A to C. And the next one is from C to B. Hopefully you agree that that equals A to B. It spans the whole entire region. So that's all this little rule says. It says the integral from A to B is going to be the same thing if we chopped up the integral and did it from a to c and then from c to b. So we went from a to c, and then we continued from c all the way to b. So both of these go from a to b essentially. Okay, so sometimes this little rule can be useful here, and let's go ahead and see this example. We are given that the integral of some function from 0 to 6 is 8, and the integral for that function from 5 to 6 is 7, and we want to find the integral from 0 to 5. So let's go ahead and use this rule. So we know that the integral from 0 to 6, just using the rule that we just said, is going to be the same thing as the integral from 0 to 5 plus the integral from 5 to 6. And the only reason I'm using 0 to 5 and 5 to 6 is because that's what's given to us in the problem. We could have used 0 to 4 and then 4 to 6, but we don't have that information. So let's go ahead and plug in now. We know the integral from 0 to 6 is 8, so we substitute that in. We are looking for the integral from 0 to 5. And the integral from 5 to 6 is 7. So all we have to do now is solve for the remaining integral because that's what we're trying to find. And that means we have to subtract 7 on both sides. And when you subtract 7 on both sides, that means we get 8 minus 7. So the integral from 0 to 5 equals 1. Okay, so pretty simple if you just know that property. Next example, we want to evaluate the integral from 0 to 2 of f of x, where f of x is shown below. So first we see that we are doing this integral for this function from 0 to 2. So what we need to recognize is that we have two separate functions. We have one function, x squared, and another function, 2 minus x. So what we're going to do is have two separate integrals, and then we're going to add the results together. So the integral from 0 to 2 f of x dx. The first function, x squared, that goes from 0 to 1. So that's going to equal the integral from 0 to 1 of x squared plus the integral, the next interval is from 1 to 2, and the function is 2 minus x. So that's 1 to 2 for the function 2 minus x. So once we have that, then we're good to go and we can go ahead and evaluate the right side of this equation. So the integral of x squared is x cubed over 3. Evaluate that from 1 to 0. The integral of 2 minus x is 2x minus x squared over 2, doing both of those terms separately. And then we're going to evaluate that from 2 to 1. So first, let's go ahead and plug in from 1 to 0 here for the first one. So that's for this one right here. Plugging in a 1, that's going to be 1/3 minus 0 over 3. So for this one, what I did, instead of writing 1 cubed minus 1 cubed over 3 minus 0 cubed over 3, you just kind of can do it in your head and say that 1 cubed is 1, 0 cubed is 0. So you can skip steps if you're comfortable with it. You can skip some intermediate steps. Okay, so the next one now, we need to plug in a 2 first. So plugging in a 2, I'm going to use square brackets for parentheses. Plugging in a 2, we get 2 times 2. 2 times 2 minus 2 squared over 2 minus, now we're going to plug in a 1. So minus 2 times 1 minus 1 squared over 2. Okay, so we have our integrals evaluated. We just have to simplify now. This is going to be 1/3 plus the first part right here is going to give us a 4 minus 4 over 2. 4 minus 2 is 2. And then the second portion right here gives us 2 minus 1 half, which is 3 halves. So we just have to combine all this together and get common denominators, and we would end up getting 5 over 6. Okay, so the integral for this function, for this piecewise function, from 0 to 2 is 5 over 6. And for the last thing that we're going to take a look at now is the definite integral as a net change of a function. So the net change of a function here is going to be this little definition that we've been using. If we're taking the integral from a to b of a function, so if we're taking the integral of a derivative, it gets us back to the original function, which is why it's written like this. But this is just the definition that we're going to be using for net change of a function. The integral from a to b is going to be the integral of the function, plug in the upper bound minus plug in the lower bound. So essentially it's the same thing that we've been doing. So for example, the velocity at time t seconds of an object moving in a straight line is v of t equals 4t minus 1 meters per second. We want to find the displacement of the object during the time interval 1 to 3. So what this means is we want s of 3 minus s of 1. So position, displacement in this case, we use the variable s. So we want the displacement s of 3 minus s of 1, the distance traveled, or rather how far away they are when time equals 3 compared to when time was 1. Okay, so this is going to equal the integral from 1 to 3 of the velocity function, v of t. So since velocity is the derivative of position, position is the integral of velocity. So we're going to go ahead and plug that in. The integral from 1 to 3 of 4t minus 1. And now we just do the math here and just integrate this. So the integral of 4t is going to be 4t squared over 2. The integral of 1 is 1t. Plug in our bounds from 1 to 3. So starting with 3, I'm going to use a bracket again. So we plug in the upper bound of 3. Well, let's actually simplify this because we can simplify 4 over 2 is 2. So 2t squared minus t from 1 to 3. And now let's go ahead and plug in our upper bound of 3. That's 2 times 3 squared minus 3 minus 2 times 1 squared minus 1. And now we just have to simplify it. So that's going to be 2 times 9 is 18 minus 3 is 15 minus 2 times 1 minus 1 gives us 15 minus 1, so 14. So what does this mean? This was position. So this means that the object moved 14 meters to the right from t equals 1 to t equals 3 seconds. We know it's to the right because the 14 was positive. If we got negative 14, that would have meant it moved to the left 14 meters. Okay, so one more question here. Based on data from the Centers for Medicare and Medicaid Services, during the late 90s and early 2000s, the federal health expenditures grew at an exponential rate with a growth constant of about 0.12. So we're going to let R of t denote the rate in billions of dollars per year of health expenditures at time t, where t is the number of years since the beginning of 2000. So a model that we're going to be using is this model right here. R of t equals 380 e to the 0.12 t. So that's just the model that we used in previous sections for exponential growth. So obviously maybe take a second and reread that paragraph just so you fully understand what's going on here. So we want to find the total amount of federal health expenditures from the year 2000 to the year 2010. And we got a nice hint here. The year 2000 means t equals 0, and the year 2010 means t equals 10. So we want to find the total amount of the health expenditures from 0 to 10. Our function that we're given the rate of the expenditures. So what we are going to be looking for, what I'm going to do is I'm going to let, let's call capital T, let T of T equal the health expenditures from time equals 0 until time t. So that means we're going to have to take the integral of the rate, r of t, to get t of t. So we are looking for t of 10 minus t of 0 because we're going from 10 to 0. Essentially the same thing that we just did. And we need to integrate this from 0 to 10. And we need to integrate its derivative. Its derivative is the rate, r of t. So let's go ahead and actually plug in our numbers here. That's going to be the integral from 0 to 10 of 380 e to the 0.12 t. And integrating this, let's go ahead and clean this up a little bit. Let's pull out that 380 because it is a constant. So now we're just integrating this exponential e to the 0.12 t. And for that, we know to do this. The integral of it is itself divided by that k value. The k value is 0.12. And now we're going to evaluate that from 0 to 10. And something that I'm going to do here just to make this a little bit easier to look at, I'm going to factor out 380 divided by 0.12. And now I'm going to plug in the limits. So plug in the upper limit, that's e to the 0.12 times 10 minus e to the 0.12 times 0. So upper limit minus the lower limit, and I just factored out the constant out front. So looks like this is going to be a calculator one. And we get 7,347. So now we have to make sure our units are correct here. So let's go back up and check what our units are. So the units for R is in billions of dollars per year. That means if we take the integral of that, our answer is just going to be in billions of dollars. So this answer is in billions of dollars. And we have that for a final answer, the federal health expenditures from 2000 to 2010 was $7,347 billion. So that's about $7.3 trillion. Okay, so that is it for this section.